Okay, hi everyone. Today I'm going to be doing a quick integration tutorial using the Excalibur software that comes with the TSQ Altis, which is a triple quadrupole mass spectrometer downstairs in the core lab in the CNRC. So this is the triple quad that we primarily use for most of our samples that need a mass spectrometer. So I'm already um, into the main menu for the software. So you can see I'm in this roadmap view that has kind of an icon for the different software that we tend to use. You're probably more familiar with the sequence setup view, which is where we actually have our samples when we're running a batch of samples. So this is kind of where we set everything up and tell it, what the name of a sample is, where it's located, how much to inject, what method to use, etc. So one of the key things that we set up in the past is something called a processing method. And so a processing method is basically it's a collection of instructions for the computer to use to identify a certain peak that is associated with a compound and then integrate it, which is kind of easier said than done. It's using the math and stuff in the background is way outside my pay grade, but it's using very complicated math to kind of figure out like, okay, if this is my baseline, when is it no longer a baseline and starting to form a peak? That's kind of the long and short of it. But it's able to automatically detect peaks for us, which is really handy. And one thing that's really nice about mass spectrometry is that in general, because we're looking for a specific ion fragment pair, we usually just get a single peak, especially if we tell it only to look in a certain time frame. So as opposed to our system upstairs in the lab that uses a PDA where we basically get an entire chromatogram and then have to, know exactly which peak to look at to integrate. This we usually get a single peak per analyte. There's a couple of exceptions that I'll go through, but for the most part, it's pretty straightforward. So the first thing that we're going to do is select all of our samples, which I've done already. We're going to go to Actions and then Batch Reprocess. And so what this does is it tells it, okay, now that everything is run, please use our processing method, which we've already specified when we set up the batch. Please use our processing method to integrate all of our samples. So we'll hit Batch Reprocess. And there's going to be a number of fields that have a check mark where you can tell it to do something. For the most part, leave that alone. This is all exactly what we want. So we want it to do, peak detection and integration. We don't want it to do calibration or quantitation at this point. And yeah, again, just leave it as it is. If you do see this one checked, I would recommend unchecking it because if you leave it checked and you hit OK, it's going to spit out an Excel spreadsheet that has all of the peak areas already for you, but we haven't had a chance to go through it. So we don't know if those are correct peak areas or not. And more often than not, there's some goof ups that happen. So we have to address those in the next step. So leave this unchecked. You'd hit OK, and then it might take a minute or two to process since we have nearly 100 samples here. So take some time for the computer to work through all that. So we'll hit OK. We've already done that before, so I'm just going to X out of it. We'll go back to our roadmap view, which has kind of all of our icons here, and we're going to go to Quan Browser. So what Chrome browser does is it allows us to actually look at the data that we generated. So in this case, I'm in our main data folder here. This is Suraj's run from a recent project that he did. So I'm going to double click on that. And that was the one that we just, batch reprocessed a moment ago. So I'm going to hit OK. And so what you can see here is we have all of these different columns here, but for the most part, it kind of looks exactly like our batch that we had in terms of the samples that we're looking at. So we have our blanks, our standard curve, and then it gets into our actual samples. And then you can see we have those, internal standards that correspond to samples from a certain day. So you can see everything is kind of set up just like our batch. But the main thing that we're really looking for is the peak area. So the peak area is what we're going to use to convert the signal that we got from the mass spectrometer into an actual quantity that we injected into the system and then eventually back into how much was in the original spinach sample or whatever food sample you're looking at. So there's a lot of columns here by default. We really don't need most of these. So just for simplicity, I'm going to turn a lot of these off. Retention time's really important, so we're going to keep that on. Yeah, peak status, sure. So let's see, calculated amount. Most of this stuff is like not even like it doesn't really even like give us anything. So I'm just gonna hit OK. So you can see that kind of simplified it a little bit. Okay, so if you look here in the right-hand side, you can see this list of compounds and masses here. And so the way I set up the processing method is that, instead of using the really long names of the compounds that we're looking at, I just use the nominal mass of the parent compound to give us an abbreviated version of what that compound is. So if we go through each one of these, you can see that the information that you're seeing kind of in this like main area over here is starting to change just as a result of kind of going through it. So what we're going to end up doing is having to go through each one of these molecules and or each one of these analytes and manually checking to make sure that the peak quality looks good. So a good peak is going to be integrated baseline to baseline. It's going to have a nice Gaussian curve. What we don't want to see is, maybe like, I'm going to show you an example here. We don't want to see anything that looks like, like this or something. That's clearly wrong. That's not the entire peak area. So the way that the processing method is set up is usually like pretty effective. Like I usually for, especially for analytes like this, I really don't see like any like major issues if we just have a singular peak. The couple of compounds that do tend to give us issues are some of the ones that have isomers. And so in the case of there's this compound here, 963.24. So you can see here, this compound, normally it's a little bit better baseline resolve. So the two peaks that we see here are usually not touching each other so much. So as a column ages, sometimes we get, less and less chromatographic resolution. So, and to be fair, this column, we have run thousands and thousands of samples on it. So it is, probably in its sunset years here. So anyway, we want to make sure that when it's integrating compounds like this, where we have multiple peaks, we want to make sure that it's not mixing up anything. So if I look in the peak areas here, we can kind of see they're kind of, all over the place. Like we have stuff that's like 1 million, we have stuff that's 200,000. So that kind of tells me that there's something going on here. The other important thing to look at is the retention time. So you can see that some of these have a retention time of 4.5, some have a retention time of 4.54. So that's a huge clue that there's some inconsistencies going on here. So you can see that in this case, some of these molecules or some of these analytes and some of these samples, it's counting both of these peaks together, which we don't want. So what we can do in this case is we can tinker around with the way that the software integrates, just to try to, tease out some of the issues that we're having here. So what I'm going to do is I'm basically just right clicking in this view here. We're going to go to user peak detection settings. So if we go to identification, that all of this information here is already in our processing method, right? So that's where this stuff is coming from. So you can see we told it that we're expecting the retention time to be 4.51. It's at 4.5, pretty good. Um, and we're telling it, what mass to look for and all that. But importantly, we're telling it which peak detection algorithm to use. So again, there's a few different peak detection algorithms that the software has built in. ICIS is the default one, but we could try using a different one to see, maybe we would have some like better luck with it. So I'm gonna go into Genesis integration here. And so if you need more, information about what these do, you can always hit the help button and it'll actually like tell you, what these different values do. The other way to do this, and I don't really recommend this just in case you end up, overriding the processing method. But if you look in the processing method itself, it'll also have like little pictures. I wish they would have it in here. I don't know why they don't, but it'll have little pictures that kind of show you the consequence of going up or down in some of these values. So what I'm going to try here is I'm going to try increasing our signal to noise threshold. And let's see what happens if I do that. I'm going to hit apply. Okay, that didn't really do anything. Let's try higher. And let's see if I try adding some of these things in. Okay, so now we're getting somewhere. So I clicked in this. I think it's really this like valley detection thing that seemed to be kind of helping. So, but the problem is you can kind of see that it's not really like catching that full peak. So let me see if we go down a little bit. Let's go to 300. go down a little bit more. I'm going to try 200 and see what happens here. Okay, let me try 150. Okay, that looks good. So I've only modified this one peak here. I haven't changed all of those. So what I'm going to do is I'm going to hit apply to all. But before you do that, take a look at the area here while I do that, and let's see what happens. And let's also look at the retention time as well. Let's see if that kind of fixes itself. So I'm going to hit apply to all. Okay, so check this out. So now all of a sudden, all of our retention times are 4.5. All of our peak areas they're not the same, but they're in the same neighborhood. So that tells me that we've probably fixed this issue, but we still have to go through each and every sample to make sure that everything's looking good. So far this is looking really great to me. So I'm going to skip ahead a little bit. Of course, you'd have to go through all of these, but I'm going to go ahead and skip over to 963.24 isomer, which is this bigger peak over here. So let's check that one out. Okay, so we've gone over to 963.24 isomer, and you can see get a little bit of an issue where both of these peaks are getting combined together in some cases. So just like before, what we can do is we can go to user peak detection settings. And I'm going to change it over to, what do we have? Is it Genesis or Avalon? I can't remember. Oh, Genesis. There we go. Okay, so we'll change it over to Genesis, and we're going to go to Genesis integration. And it seems like this valley detection is really like kind of the main thing that seemed to help. So I'm going to hit apply to all and see what happens. Okay, okay, this is looking good now. So we're not getting both of those peaks combined together anymore, which is terrific. Excellent. Okay, so again, you would have to go through each and every sample, each and every analyte, make sure everything's looking good, kind of go through that process. And again, I want to emphasize for most of these, like 95% of them, you're not going to have to tinker with anything. It's very straightforward when there's just a single peak. This is kind of an exceptional thing. So anyway, we're going to go ahead and save. And so this is something that you want to do ideally at the beginning, but we want to save because this is going to keep all of that information that we are, kind of, or all of this data that we're kind of curating here in one file. I've already created a file, so I usually just save it in the same place where the samples are, and I'll give it a name that, is descriptive, and so we can go back to it and easily find it. And I would recommend maybe every couple of analytes or so going through and saving. So that way, if you get booted off or if the software crashes or something, you don't have to start all over again. Because again, this whole process can take like a good 30 minutes or so. Okay, so let's say that we're all done here, and now we want to go to the next step, which is where we can actually start working with these peak areas. So what we want to do is we want to go to File, export data to Excel, and we want a long Excel report. That's going to give us kind of all of the information that we need moving forward, and frankly, more information than we need. But the short report just doesn't have enough. So we're going to get an Excel spreadsheet here. And I'm going to go ahead and I'm just going to save this because right now it's saving onto the computer, the computer that this instrument is connected to. And so what we want to do is actually save it to our lab folder. So I'm going to go into our data, flavonoids. This is again, this is a Raja's project, and I'm just going to overwrite this file here. Perfect. So now it's saved into our shared drive. So that way, if someone else needs to use the mass spec, we can jump off at this point. We no longer need to be on this computer. And so what I want to highlight to you here is that in these reports, instead of getting all of the peak areas in one place, you have each compound gets its own tab, which is kind of annoying because when we actually go to quantitate things, we're going to end up having to merge all of these peak areas together. So I'm going to show you how to do that in the next video, but that's going to be coming up shortly. And I think the other thing I want to emphasize here is that the samples are no longer in the same order that they were in the integration software. They put them in the integration software, they were in order of the actual like batch that we ran. And I'm not sure quite how to do this, but yeah, I've tinkered with the software a little bit, but never been able to figure out how to get it to just export it the same way. But it just puts it alphanumerically. So it's just an order of the sample names. So that's important to keep in mind for the next step where we're going to have to kind of do some data wrangling to kind of organize everything together into a single spreadsheet. So we will touch base in the next video about that. Okay, so this is kind of part two in terms of trying to figure out how we can go from the data that we get off of our mass spec into something we can actually use and work with. So I mentioned before that we have kind of a template that allows us to take all of this, all these peak areas from these individual molecules that we look for flavonoids and spinach, and actually put it into a format that we can work with. So I've already kind of gone ahead and done most of these, but you can kind of see here that we have a column here for the sample name and date and rep number. And it's in the same order that's in that spreadsheet that the software produced. So that way everything is kept lined up and together as it should be. And then we have some additional built-in formulas that we'll go through in a little bit. But for now, I'm just going to kind of show the process of getting those last few columns ready. So here we go. So we've got, yeah, 327.05. So I'll go into the area here, write down, copy and paste, 357, copy, paste, and our last one, 313. Okay, so I mentioned that, when we run our samples, we extract in batches, and so each batch has its own internal standard. And the way that this software spit out the samples to it was in numerical order, so it kind of like lumped all of the internal standards down here, which is not super helpful for us. So what we're going to do is we're going to do a little bit of we're going to do a little bit of like an Excel trick here to get this fixed. So what I'm going to do is open up our original batch file. So I prepared this in advance before we ran the samples. And so what I'm going to do is minimize this that way. Okay, there we go. So I'm going to find I believe it was here. Perfect. Okay, here's our batch file. Okay, so this was the Excel spreadsheet that I created to upload into that mass spec, so that it would automatically kind of know where all of our samples were, what method to use, et cetera, et cetera. It's basically the sequence setup, but just in a spreadsheet. So what I'm going to do here is I'm going to do a little trick. So just going to insert numbers, or actually, we can probably just take advantage of we already have a sample ID column. So I'm going to do 1, 2, 3. All right. And then I'm going to highlight this and I'm going to double click. So now it's all the way, you can see 1 through 97 here. So what I could do is I can go in here, I can go data sort. I'm going to sort by sample ID. So it's already in sample, or I'm sorry, not sample ID. We're going to sort by file name. So you can see now it's sorted in the order that the software spit it out to us in. So you can kind of see it's not in the original order anymore. Now it's just in numeric order by the file name. So what I'm going to do is I'm going to copy this. I'm going to go back into our spreadsheet here. Oops, I don't want to insert copied cells just yet. Okay, close out of this. Oh, copy this. Paste this down. I'll just say, yeah, sample ID. Okay. So we can go ahead and, yeah, let's close the other spreadsheet, and we're not going to save that. Nope. Okay, so now we've got this sample ID in here. So what we can do is we can go to data and we can sort it just like we did the other spreadsheet. We'll sort it by sample ID. You can see now it's back in the original order. So there's just kind of like a little Excel trick. So you can see how it's, we have this was our first day of extraction. These are the internal standards, then the blank, then the second day extraction, then the internal standards, and then the third day. So everything's kind of in the correct order now. So now what we can do is we have to start correcting these peak areas for extraction efficiency. And so I'm going to come back in a little bit and we will get back into that. Okay, we're back. So previously we ordered everything into the original order by which or in which we ran them on the instrument. And so we have everything kind of grouped into those little chunks of three, which correspond to those three different days that these samples were extracted. And so that way we know which internal standards belong to which set of samples. Okay, so let's talk about how to, oops, let's zoom in a little bit. How to go from our raw peak areas to a internal standard corrected peak area for extraction efficiency, and then a second layer of internal standard correction for the mass spectrometer. So in the case of flavonoids, for spinach flavonoids at least, we have two internal standards that we add for recovery or extraction efficiency. One is naringin, which is a flavone that's found in citrus fruits that has a couple of sugars on it. And the other is naringenin, which is the aglycone or sugarless version of naringin. So these are different polarities. Naringenin is more kind of semi-polar, whereas naringin is very polar. So it kind of helps, give us some different ways of figuring out extraction efficiency depending on the compound that we're looking at. Generally speaking, most of our compounds in our samples are very glycosylated and decorated, so we use naringin to estimate recovery. Okay, so these are all of the organized peak areas that we've put together here. So what we can do now is correct for extraction efficiency. So kind of one of the most like basic ways to do it is to take the peak area of naringin in a given sample and divide it by the average of the peak area of naringin in our dummy samples. So we get, in this case, we get 94%, pretty good. And we kind of go down the line here for each sample. And we can also do the same for naringenin. And in this case, these numbers are a little bit goofy because in that first batch, looking at my notes here, it looks like the only naringin was used and not naringenin. So you can see it's basically just kind of bogus numbers. It's just kind of like trace peaks that the instrument was picking up. So can kind of ignore that for now. But regardless, the let's see, where'd that number go? Cool. Okay. Regardless, we basically have our extraction recovery here. But the thing is that this doesn't necessarily hold true on a mass spectrometer. So on a mass spectrometer, we have each sample, there could be kind of random variation just from the instrument itself. Mass spectrometers are notoriously unstable because of the quality of the nitrogen coming in or the flow rate or the temperature. Most of that stuff is pretty stable, but especially with triple quads, you tend to see a little bit of drift throughout the day as your source gets a little bit dirtier with each run. There's kind of like matrix factors that accumulate on the source and kind of diminish the ionization efficiency that you get. So we actually have to correct these values for that instrument noise. And so that's where that third internal standard comes in that we add in when we're redissolving our samples, which is taxafolin. So this isn't naturally in spinach. So adding it, anything that we see is going to be from what we added. And so we add this in to kind of help understand how the background and the background of our samples and the instrument itself might be affecting the signal that we're seeing. And so what we can do is we can basically take so in this case, we're using naringin again. So we take our naringin peak area, divide it by the taxafolin peak area in that sample, and then divide all that by the average of our naringin peak areas divided by the average of our taxophilin peak areas. And so we end up with, a little bit more of a kind of realistic extraction efficiency here. Okay, so we've got our extraction efficiencies kind of worked out now. So what do we do with that? So, moving over in the template here, I have some formulas set up where we're basically just taking our peak areas and dividing it by that recovery. So you can see that we had, I think 11,000 here, but the recovery was only 78%. And so if we divide that 11,000 peak area by our recovery value, we get 15,000. And basically kind of, it kind of simulates what that peak area would be if we had 100% extraction efficiency. So we go through and we do that for all of our analytes here. And basically kind of, pull that down and pull it across so that everyone is getting corrected. And you can see I'm using the dollar sign here to kind of help make sure that as I pull across, I'm still pulling from this value over here. But I don't have a dollar sign after the 15 or before the 15 here, so that way when I pull down, it stays in the right column, but it just moves down into the correct row. So everything is kind of, linked nicely. So always just double check that to make sure. Speaking of double checking, one thing that I also found was that for one reason or another, in this example batch that I'm working with, these two samples, 2348, 1 and 2, were actually part of batch 2. And so what ended up happening was, let me put it back to how it was before. So we have, it's looking like a 90% recovery there. So what was happening was that the formulas were using these internal standard values, which are from the first day. And look what happens when I put it back. You can see our recovery is 160%, which doesn't really make sense. So what ended up happening was again, these two samples, they were actually run in the second extraction day, but they accidentally got lumped in with the first day. So I had to, make a manual change there in order to get the correct recovery. So we can just go back in. Let me see, it's not saving it. So we'll say that these were part of batch 2. And so we'll move the naringin and the taxophilin values to the internal standard samples that were for extraction day 2. And you can see the recovery is now at 91%, which makes much more sense. And again, it's a huge lesson in terms of why we need to keep those internal standards separate and why they need to be with their own batch because day to day they can change just based on, oh, maybe somebody, made a batch differently or it was sitting out or it was freeze thawed too many times. It's going to be different, a little bit different every time. So we always have to make sure that we're using the correct internal standards with the samples that they're paired with. Okay, anyway, so we've got our corrected for extraction efficiency, corrected peak areas here. So this is kind of simulating, batch 1, batch 2, batch 3. This is simulating what would have happened if we had 100% extraction efficiency for every sample. So the last thing that we need to do is correct for the instrument variation. And so I mentioned that we use taxophilin to correct for any, variability that we see in the signal sample to sample. And so all we have to do is just take our extraction efficiency corrected peak area and divide it by the peak area for taxophilin, which is our internal standard. And you'll see that instead of getting, a number that's in the thousands or tens or hundreds of thousands, now we're getting kind of a decimal, non-whole number. So you can kind of see just visually looking through, some of the analytes that are larger, they might be like a small whole number, and then other ones, most of them are just kind of decimals. And so this is where we're at in terms of, our final peak areas that we can actually use for analysis. And so we have these corrected for both extraction efficiency and instrument variation. And so when we compare them against a standard curve, we will also use the standard curve will also be done using not just the peak areas from each of those individual standards, but from the corrected peak areas using our taxophilin. So just to show you an example of what that might look like, if we do this divided by taxophilin, you can see that the the actual, quote unquote peak area that we get for each of these samples is, much smaller. So now when we saw those samples where the peak area was, like a small decimal or, around like 4 or something like that, we know kind of where it falls within that standard curve. So again, using taxofolin to correct for instrument variation is really key to getting more consistent data and actual usable information out of mass spec runs. You can run without them, but it's really, really risky. And from my personal experience, you usually get garbage data. So that's why we have to use these internal standards. And that's why it is so critical that during the redissolve steps, we're very, very careful to make sure we're adding exactly the same amount of taxofolin to our samples and using standard curves that are made with the same taxofolin that we're using to spike into our samples. Okay, so I wanted to give you guys a tour of the quantification template that I recommend using for flavonoids, and you could probably adapt it for other things as well, but you just have to um, check with me first just to make sure everything's kind of lined up okay. So if you go into our shared folder here and you go into data, you go into quantification templates. I have a flavonoid quantification template that is all ready to go. If you're going to use this template, please save it as something else before you start making modifications to it for whatever sample set you're working on. And so anything in orange kind of indicates it's something that you need to change. And so, starting up here, we have all of, if you go across the columns here, these are all of the analytes that we're looking at for flavonoids. And below it in row 2, we have all of the molecular weights, which we use in a future calculation to go from moles into milligrams. So we need that grams per mole quantity for each analyte that we have. And then I've set up this spreadsheet for, a very likely scenario where you've had to run samples on multiple days. And so, we talked about in the last, couple videos looking at, converting our peak areas into more normalized peak area based on taxofolin as our internal standard. We talked about how mass specs are pretty variable day to day, and even within a day. And so, this is certainly the case if you're looking between days or, sometimes you're running samples weeks apart. We always have to run a standard curve with a batch of samples to take into account any changes in the instrument. So you can see up here, I have 3 rows. This is, I think this was just kind of left over from a project that I snagged this from, but, 3 different individual rows worth of standard curve slopes. And so you can see that most of them are the same number within a row. And that's because we quantify almost everything to quercetin 3 glucoside, which is a common approach that people take because spinach flavonoids just aren't commercially available for purchase except for the aglycones. So you can see, in this case, if you were working in your real template, you would have to delete this value and put in the value of your slope to automatically populate these other columns here. We do also have a few aglycones that we run with our samples, such as patuletin, spinacidin, naringenin is standard or internal standard for extraction efficiency, but we usually throw that in too. And then also jacidin. So these actually have their own individual standard curves, but the rest of them are all just kind of mirroring whatever goes into the quercetin 3 glucoside column. Okay, moving down, we have our serving size here. That's something that, it's kind of up to you if you need to change that, but yeah, for the most part, that's a standard value like milligrams per 100 grams. But yeah, sometimes we'll use like 30 or something if that's the like USDA serving for something. Moving down a little bit more, we have our sample weight, which is something that's already been recorded in our shared folder. Then we have the batch date, sample ID, and technical rep. And again, I split this up into, we have kind of like 3 components here. So each, the peak areas that go into this, first chunk here would be using this slope, these slopes in row 3. In the second chunk, they would be using the slopes in row 4, and the third chunk, they would be using the slopes in row 5 to go from a peak area to an actual like moles on column, and then eventually like moles in your sample. So that's kind of the bulk of the template here. The other thing I want to show you is the standard curve area. So we adjusted all of those peak areas in our in that previous spreadsheet for our actual samples, but we also have values for our different standard curves. So these would just get pasted into here along with the taxophylline. So I should probably make this orange too, so you can kind of indicate that those need to be filled in. So yeah, so for each compound, so we have naringenin, quercetin 3 glucosides, spinacidin, jacidin, and pachyletin. And the formulas are already set up to calculate everything. And you'll see I'll show you an example of an actual standard curve in a second, but you can see up here too, this is an opportunity where you need to write in, what your mobile phases were, what your column was, and, the date. And again, I also echo, putting that down here as well in the actual tab so you know when it was run. And it's especially important when you have multiple standard curves that you're able to keep track of which one was which. So here's an example of kind of a filled out standard curve. So you can see I've got the date and all that information up here. Got my, for naringenin, for example, I've got my original peak areas, and then I have the taxophylline peak areas as well. And so I have, for every standard curve, I have two linear models that I set up. So one is just using the uncorrected values, and it's just something that, I just kind of do it just because it's nice to take a look at, just kind of make sure things look normal. We don't actually use this slope because, again, it's not corrected for taxophylline. We end up using this one over here. So quick algebra reminder. So in a linear model like this, we're kind of using that standard equation y equals mx plus b, where m is the slope. And so, if we look closely here, if we wanted to get the slope of naringenin, and again, this is taxophylline corrected, all we'd have to do is just copy this number here. We'll hit copy, and we'll pretend, we go over to, we find our naringenin over here and we would paste it. But then also remember that when you copied it, that was grabbing an X as well. So like that X makes it not a number anymore when you paste it into a cell in Excel. So you'll have to delete that. So you can kind of see up here where I'm moving my cursor. That's the actual peak. That's the actual slope that you would want to put up in there and delete that X. Okay, so that's really like the main thing. The other important thing that I want to emphasize before we move on to the next part is this is just a template. Please don't overwrite it. This is supposed to be kind of a legacy copy. So what I would suggest is if you're starting a new project and you're using this template, immediately save it as its own, give it a new name in a different location so that way you can easily, manipulate it however you want. And if something gets messed up, you can always go back to the original. We want to keep this as a legacy copy so that we know the all the formulas and stuff are intact. I guess, yeah, why not? We're here. The only other thing I want to just kind of briefly mention is that there's some filled out formulas kind of to the right here. So this area that's empty, this would be where your peak areas would go for a given sample or set of samples rather. And then we have it already set up to automatically convert those peak areas into moles per serving, or that, in our case, we used 100 grams. And then we convert that into milligrams per 100 grams using those molecular weights. And then if you did an in vitro digestion and you need this, you probably won't need this, but this is just kind of a secondary equation that kind of helps determine how much was in that in vitro digestion tube, but you probably won't need that. And again, there's an area here where you would insert your sample mass if you were doing an in vitro digestion and had those sample masses. Those would be saved in the spreadsheet that has all of the like homogeneous weights and whatnot. The only other thing that I added in here too, this is just kind of like a little like bonus thing, I guess, but sometimes it's kind of nice to just look at the contribution of like an individual flavonoid versus the total. So I have you can see there's like a couple rows here between some of these chunks of future data that will basically convert, like it'll take like an average amount and then divide that out of the total over here. So you can kind of see like, oh, this flavonoid is like 20% of all the flavonoids in our samples or something like that. Just another metric you can use to kind of interrogate your data a little bit. Okay, we're back. So copy this over and paste right in there. There we go. Nice and lined up now. Okay, perfect. So now we have our peak areas pasted in. And so one thing we'll have to do is pull down these formulas because, yeah, again, I didn't do all of that yet. So we can go all the way across here. Um, okay. And then we will pull down how many it was. Oh, didn't even catch all of these. Excellent. Okay, we just need one more row. Okay, perfect. And then same with over here. Gross mistake. Perfect. Okay. All right, so we've got that set up. So now what we need to do is actually fill in some of the information that we're missing here. So I'm going to move my inset here. Okay. Shift control. Okay, so we've already done this. So that's easy. Boom. Okay. Now what we need is to get these sample masses. So we can find that in, let's see here, our data entry sheet. So every project has its own spreadsheet. So we've got our sample weight here, and just ignore this. This is for wet tissue. So this is our sample masses. Now we have it in grams. Oh, that's right. We have it in grams. So we're going to have to convert that real quick. So what I'm going to do is equals this. That. Then we'll paste the values in because it's an equation. Perfect. Okay, so there's our mass there. And then the next step that we have to do is to actually like fill in our standard curves. So just for the sake of time, I'm just going to do the quercetin one for today. So what we're going to do is we're going to go in here and we are going to fill out this information that we need. So we will open up our old spreadsheet here. We'll go into here. So let's look at, so we've got quercetin 3-glucoside. Copy that. Okay, and then we'll go back to get the taxofolin values. And what's nice is once we get the taxofolin values, we can basically just paste those in for each one of them, because again, we use it's the same thing for each one of them. And normally we have a 6561 full diluted stock, but we didn't include that in this particular run. So that's why that one value is missing there. Okay, so we now have our slope. So I'm going to hit copy. We'll go over to here and we will paste that in up here. Paste. Okay, and so you can see that we have that X in there, so we just have to delete that X so it becomes a number. You can see here now we're actually like getting numbers over here for the most part. So it's automatically calculating, it's using the slope of quercetin 3-glucoside to estimate pretty much all of these glycosylated flavonoids. Now, there's a handful here that we'll have to just snag the slope for, but that's just the same process as we did before. So we just have to grab the peak areas from the original spreadsheet that we had where we merged all of the peak areas together into a single spreadsheet. And then just paste the slope here and remove that letter X at the end so that Excel treats it as a number. So from here, we basically have our, if we scroll to the right, we have our actual milligrams per 100 grams estimates over here, which is terrific. And you'll see that, we have like some, I think we have some columns that are totaling things together. And we have a few values that are registering as divide by zero just because we haven't put in the slopes yet and or there might be some like missing values. And so that's something where some of those can be either converted to, you can convert them to like another, like a zero, for example, if you wanted, or you could use another approach people take is that they'll sometimes use like 10 times the limit of detection for a certain compound as a way to impute that missing value. So I think from there, that's pretty much the start to finish of it. Yeah, I think that's pretty much how we go from integrating on the TSQ Altis all the way to actually having quantification data. Okay, one last topic that I wanted to talk about is how to go from our quantified values all the way to something that we can actually analyze. So what I did was I made a separate tab in our spreadsheet here, and I called it Siraj Salinity Stats. And so all I had to do was, and again, this is why we set up the spreadsheets the way that we do. All I had to do was copy this information down. So the treatment, variety, sample, and replicate. And then I pasted in all of the different analytes that we have at the top here in row one. And so what I did was I went into here. I essentially just selected all of these values, copied them, and then pasted them as values. Because again, there's equations built in, so we just want the numbers. One thing to bear in mind that I think is we might modify the template in the future so that it doesn't have this, but we don't want to really include like naringin or naringenin because those were internal standards that we added. There's also some like kind of vestiges from some other things, like there's ethyl gallate here. We can get rid of that. And same with taxofolin. So at least for now, what we can do is we can just go in here, we can delete ethyl gallate. We can delete, oh yeah, and then quercetin 3-glucoside. That's our external standard that isn't actually in our samples really. Naringin, we can delete. Naringenin, we can delete. And I believe that's it. And then we can also, oh yeah, we could do a total here. Just do some and A2, AR2. Great. I'll just click that down. Great. Okay. So yeah, and by the way, these numbers are huge. So part of that is because we're doing this on a dry weight basis. So this is basically ready to be used for statistical analysis. So we would just want to save this as like a .csv file. So it's just a standalone comma delimited file. So let's just do that now. Save as. We're in quantification. And so I'm just going to say, let's like click in here. Let's see, let's do that. Stats. There we go. And then I'm going to save that as a comma delimited, comma separated values also works, but you want it as a CSV file. So that way programs like R can open it up. Hit save, hit OK. And then you'll see if we look in that, so you can go in here. If we look in here, you can see now that because it's a CSV file, it should only, or yeah, let's exit out of this. There we go. So it should just be what we did. So you can see how it kind of collapsed like some of the formatting and stuff we had. It makes it like very simple and readable for statistical software. So you can see we've got our treatment, variety, sample, replicate, and then all of the actual data for some of these different molecules. So yeah, we'll be able to analyze these data now.